Good morning and good evening wherever you are. We'll get started really quick today with 10.5, inscribed angles and polygons. Inscribed. What does it mean to scribe something, guys? What does it mean to scribe something? If you scribe something, if you're scribing something, you're a writer, right? You're writing for it. Okay? You're writing something. What's in mean? Inside, right? It means inside. So if we can think of it like that, like in means inside. So inscribe is scribe in. We're writing the angle, an inscribed angle. That's our first word, by the way, an inscribed angle is an angle that's scribed inside. I'm going to write this. I think of it like this, an angle written inside the circle, an angle written inside the circle. Okay? So to mathematics, to be very precise, all we're going to say is it's an angle, right? An inscribed angle is an angle whose endpoints and center, whose endpoints and center, whose angle and center are on the circle. Okay? How can I draw that? So I'm just going to pick 3 points on the circle. Okay? Here's an endpoint to a vertex. Here's an endpoint to a vertex. That's an inscribed angle. This angle is written inside the circle. Do you guys see kind of why it's called an inscribed angle now, right? The angle is contained entirely inside the circle, right? Entirely inside the circle. So look, it's really, you can think of it like the angle between 2 chords, right? If that helps you out. Maybe here you want to write it's an angle between 2 chords. Between 2 chords. Very cool. Okay? So the next one, we can talk about the next one we're going to need, is something called the intercepted arc. So intercepted arc. Okay? This is just an arc. It's an arc, but it's on the inside. It's on the inside. An arc, I think of it like this, on the inside of the angle. On the inside of, well, let's say on the inside of an inscribed angle. The inscribed angle. So an arc on the inside of an inscribed angle. Okay, we can also think of it like this. If we're being very mathematically precise, it's an arc intersected along the inscribed angles. This is a very complicated definition. The inscribed angles interior. The inscribed angles interior. And that's just the part of the angle we actually measure. Okay, so not really thinking about the strict mathematical definition right now. We're thinking of it in terms of this guy, right? Thinking of it in terms of this one. We can look at it like this. It's an arc on the inside of an inscribed angle. Okay, so here's the inscribed angle. Okay, let me get a new color. Okay, the angle this guy points to is this right here, right? Angle of this guy points to is this right here. This orange bold line here. That's the intercepted arc. It's the arc that's on the inside of the inscribed angle. It's being intercepted by the angle. It's the intersection of this angle projected out. Do you guys see that? Onto the circle, okay? So whenever we talk about the intercepted arc, we're talking about the guys that are the arc that is inside of that angle right there, okay? Very cool. Okay, so coming down to these 2 theorems, let's read these, and I encourage you guys to pause here and try and figure these out on your own. Maybe not prove them, because they're a little bit tricky, and I'll show you guys how to do that in a sec, right? But just think about what should go in each of these blanks, what should go in these blanks, okay? So, the measure of an inscribed angle is exactly blank the measure of its intercepted arc, okay? Pause here and try and figure that out. All right, after you've thought about it, you might see, if you drew a line like this, right? Drew a line like this, look at this. This angle here is the same as the measure, let's draw it like this, the measure of this arc, right guys? Same as the measure of this arc, okay? This arc is the same as that interior angle, so now, not interior angle, but a central angle, okay? So if I can imagine myself taking this point that this angle is connected to, and then dragging it a little bit farther away, right? And then dragging it a little bit farther away. dragging it a little bit farther away. We all agree that it shrinks, right? That angle gets smaller and smaller as it gets to this piece. Okay? Very cool. Something cool about this is that you can think of it like I've traveled from here to here, if I'm thinking of this angle as moving, right? Like this, right? From here to here, if I'm going in this direction, I've traveled r, right? Well, if I go another r away, right? If I move that angle another r away, let's erase all this clutter now. If I go another radius away, I've gone twice as far as I started. And since that angle is shrinking, right, this angle should be exactly 1/2 the measure of its intercepted arc. This angle is 1/2 the measure of its intercepted arc. Okay, so now we're going to go ahead and prove why this works. Okay, and this takes some serious algebra. All right, some serious algebra. So what we're going to do is draw a line, and we know these are radii, so these guys are equal. Okay, now look at this triangle I've created. This triangle, maybe I label it A, B, C. This triangle ABC here. Okay, this triangle I've created is isosceles, and so its base angles are equal. Right? Do you guys see this? This angle is the same as this angle. All right. What does that mean? That means if this angle is x, then this angle is x. Okay, and this angle here is what? It's 180 minus x, right? Minus 2x. 180 minus both of those pieces. Okay. So that's a measure of that angle. If I come over here in orange and I mark this angle, this is the angle I'm trying to find. Why? Because I'm trying to know the measure of this arc, right? I'm trying to know the measure of this arc. This arc is also angle y. Measure y. Okay? So, thinking about this in terms of y, I want to solve for y, right? Well, using supplementary, I can get that this guy, y is equal to, I can write this equation, and I'm going to write it inside the circle, okay? I can write that y is equal to, so y is equal to 180 minus this angle. 180 minus this angle, which is what? Which is 180 minus 2x. Okay, so I'm just plugging in this angle. Do you guys see that? I'm just plugging in this angle. Maybe I'll write my y in orange and this angle in blue to help us out. Maybe you can see what's happening. My y right here, and same exact thing but in blue, 180 minus 2x. Okay, check this out. What I can see now is how do I solve this guy? How do I solve this guy for y? Okay, 180 minus, this minus distributes out, right? So I'm going to get 180 minus 180 plus, that sign's going to flip, 2x. What's 180 minus 180? Oh, it's 0. Exactly, right? So these guys cancel. Oh, and so you're left with y is equal to, and maybe I should have left this as blue. Y is equal to, and then we'll get 2x. Y is equal to 2x. Look at that. That's exactly right. So the measure of x, the measure of this angle x is exactly 1/2 the measure of y. Okay, and y is the measure of this arc. So x is exactly 1/2 y. That's exactly what we wrote. That's exactly what we wrote up here in the theorem. All right, so thinking about this next one, if two inscribed angles intercept congruent arcs or the same arc, then the angles are what? The angles are what? They must be, if you pause it here and think about it, they must be congruent. They must be congruent, right? How can we show this? Okay, how can I show this? Guys, this picture looks tricky. This picture looks weird and wacky and confusing, okay, but it's not that bad at all, I promise. This green line here, this green arc, okay, if this guy is like 100 degrees, I don't know what it is, right, but if we just call it 100 degrees, okay, then this inscribed angle is half of that, so it's 50. Then this inscribed angle is the same exact thing, right? It's the same exact, like, deal I'm looking at. This is also 50, okay? That's because both of these guys, just like the last definition we used, both of these lines, look, are intercepting the same arc. Do you guys see that? Both of these lines, I want it to go away. Both of these lines are intersecting the same arc, both intersecting the green arc. So the I think it's red and black are both intercepting the green arc. Okay, cool. So, and these are not necessarily 100. It could be anything, right? So that's not really a proof, but that's kind of thinking about it in the right way, right? Okay, so let's do a couple of examples. This first one is not too bad. Find each angle or arc measure. Okay, so it wants the arc of JML, the arc JML. So if I come over here, where's arc JML in this picture? I'm going to go from J to M to L. Notice it specified 3 letters. That means I want a major arc, right? So I'm not going this way. I'm going all the way across. So JML, just like that. The measure of that arc must be twice this number by our previous theorem, right? Twice 88 degrees, okay? Well, the measure, I'm just going to write it out like a formula for us. Measure of JML is equal to twice 88 degrees, okay? 2 times 88, that's 160 plus 16, or 176. 176 degrees. So not quite 180, right? Not quite 180. So actually, you can say that this arc is only 2 letters, but it's so hard to tell. We just gave it 3 anyways, right? So it's kind of like we had questions about in class on Monday. All right. So this next one's not too bad either. I see this piece is 34. I see this piece is 34, right? So what I want is to find the measure of ABC. So I want to find the measure of ABC. Where is ABC on this picture? It's right here. It's right here, right? This is my angle I want. I angle A to B to C, okay? So this guy's 34, and I want half of him to get to this angle. Look at how this angle is smaller than the central angle. Do you guys see that? That's how you know I'm going from big to small. I'm going from big to small, so I'm going to divide by 2, okay? So I'm going to say the measure of angle ABC is equal to 1/2 of 34 degrees, which is exactly, almost messed that up, 17 degrees. Okay, 17 degrees, nice. So right here, we'll put 17 degrees. As easy as that. It's as easy as that, guys. Okay, so we're going to do a couple more theorems. I think we got 2 more and we're done. Okay, what happens when an inscribed angle's intercepted arc is a semicircle? What happens when an inscribed angle's intercepted arc is a semicircle? That's a lot of fancy math language, right? That's a lot of fancy math language. All we're saying is, what happens when an inscribed angle, so here's my inscribed angle. What happens when an inscribed angle, like this guy right here, its intercepted arc is a semicircle. So look at this. This guy is a diameter, so it creates this semicircle. So the intersected arc is what? It's 180 degrees, right? So that means this guy, and if we draw this in now, we're ready, right? This guy must be what? Excuse me, I shouldn't have drawn that, but you guys know what it is now, right? This side is 180 degrees, so half of that is 90 degrees, right? So right here, we can come down here, and intercept arc, and that angle is a right angle. Or if you want to in this blank, you could just write 90 degrees, same thing. A right angle, 90 degrees. Okay, cool. That makes sense, right? I'm talking about half of the semicircle. I'm talking about half of the circle. So this whole side is 180, so half of that must be 90, just by our previous theorem. Okay. The next one. What do you notice about opposing quadrilateral angles in the inscribed quadrilateral? What do you notice about opposing angles of the inscribed quadrilateral? Okay. What is an inscribed quadrilateral? What does inscribed mean? Well, inscribed, like we talked about earlier, means written inside. So look, here's the the quadrilateral, the 4-sided shape, the quadrilateral. That's drawn inside of this circle. That's what I'm talking about right here. This is the quadrilateral I'm looking at. Okay. Here I've pointed out to you some opposing angles. Okay. Now, if we think about this, what do we notice about these opposing angles? Okay. I want you guys to pause the video and think about this one. Okay. Think about this one. So I'm going to use a little trick here to show you guys something on the actual, since I'm doing this on an iPad that I won't be able to do in class. Okay. If I sketch this angle out like this in blue, let me get a little bit closer for the demonstration. If I sketch this angle out in blue, look at those tracing skills, kindergarten raised me right. So I can take this piece here, I can move it around. You guys see that? So I can move this angle around and I can figure something out that's pretty cool. Look at this. Let's see. I don't want you guys to see. I don't know how I can rotate this. Maybe it won't work. Well, that's saddening. So it won't work. Just kidding. Okay? But what we can see here, what we can notice, is that look at this first, and we'll do this guy in orange. Look at this first orange arc. This guy intersects what? It intersects this piece of the circle. This piece of the circle. Okay? This blue guy, its intercepted arc is this piece of the circle. Look at that. Okay, so if this guy, if the blue one here is intersecting this piece of the circle, the orange one's intersecting the other piece of the circle, and the whole circle is 360, then if I took a piece of that, if I was dividing it up into 2 pieces, I would want half of that, and then this angle is half that again. So what I'm saying is, this angle is half of this arc, right? This angle here is 1/2, and I'm just writing this loosely. This is 1/2 of blue arc, okay? This right here is 1/2 of orange arc. Okay, so what we end up getting is that the opposing angles of an inscribed quadrilateral are supplementary. Supplementary. Okay, and that just means what? That means they add. That means they add to 180 degrees. Okay, very nice. Very nice. So we got 2 examples, and then I think we are. Yeah, we have 1 more, and then we're done. Oops. Okay, so think about this in terms of what we were just talking about. Okay, if this guy is 43 degrees, and well, actually, let me ask this first. I'm trying to get to this. I'm trying to get what that these. I'm trying to find a value for x, right? Okay. If this guy's 43 degrees, then that means this guy here is what? What is that guy here? He must be. Well, must be twice that. He must be 86 degrees. Okay. Must be twice that. It must be 86 degrees. Okay. Well then, this guy is a diameter. Let me draw this in orange, maybe. This guy right here, SVT, is a diameter. Okay. So that means this angle must be a right angle. Right? So if that's a right angle, what do I know about this last angle? What do I know about this last angle here? Let me zoom in a little bit. That'll help us out. Okay. This last angle right here, this angle must be 180 minus 43 minus 90, right? I'm just subtracting both of those angles. So I'll get 180 minus 90 is 90, right? And 90 minus 43, excuse me, I didn't mean to write this whole thing. 180 minus 90 is 90, so 90 minus 43 equals, right? And we'll write an equal sign here. Okay, 90 minus 43, that is 57. Okay, that is not 57. That is 47. Excuse me, guys. 47, right? Because 7 plus, yeah, okay. So then, what we'll see, if this guy's 47, what do we know about the measure of this arc? What do we know about the measure of this arc? Well, this arc is what? This arc is 9x minus 14 degrees, right? 9x minus 14 degrees equals, this must be twice 47. Must be twice 47 degrees, okay? So, if I solve this guy for x, what I'm going to do is, and now I drew this intentionally so that we could see. Here I'm talking about degrees, so my answer is going to be in degrees, okay? So I can just ignore these guys. I can just ignore these guys for the time being, okay? What I can do is I'm going to get 9x minus 14, just rewriting it without the degree sign to avoid confusion. Okay, will give us, let's see, this is 94. Okay, so add 14 to both sides first, right? I'm going to get 9x equals, and then on this side, I will get 108, okay? And then x is equal to, and luckily that perfectly divides 9 by 11, right? Look at that. Or, I'm sorry, not 11, but 12. Okay, so x is 12. Look at that. X is 12. Okay, so that's how we figured this guy out. This is like 3 steps. That one's a pretty tough one, right? So if you can do that one, you can do them all. Okay, check this one out. I want to find the angle 7x plus 21. Okay, well, I want to find x. All right, here's what I'm looking at. I have this guy's 47. He's across from this other guy. We just had a theorem that said those guys are supplementary. What does that mean? That means they add to 180, right? So this angle, 7x plus 21 plus, so I'm just going to keep them in parentheses for simplicity's purpose, right? This guy plus 47 is equal to 180. It's equal to 180. Okay. So remember, since we're dealing in degrees, we can think of it as not having degree. We could put degree back into the end. Okay. So what we'll get here is we will combine like terms. So we'll get 7x plus, and we'll get let's see, 8, and then we will get 6. So that's 68 equals 180. All right. 7x equals, and then 180 minus 68. I encourage you guys to try and do these without your calculator and then check your answer. Okay, we will get 100 and let's see, I think I just messed that up in my head. 112, that's right? Okay, so 112, and x goes into 112. I don't even know. Here I am saying to use your calculator, and I don't even know. So if we plug this into the calculator, against my own words, we get 16. Okay, look at this. This is 16, so x is exactly 16. Okay, when you're doing your homework, don't be discouraged by decimals. As long as you believe in your answer and you've done your math correctly, okay, a decimal is okay. All right, you guys remember that as you're working. So that's you do those two. This last one for today will be done. Will be done, and you guys can finish this question here on your own. Okay. So what we want here is find the measure of the shown angle. So this is the shown angle. This is what it means, right? What can I do to find this guy out? So this guy is 20. This guy's 20. Excuse me, not that. That's not what I meant to write. This arc here is 20. This arc here is 70. Right? So altogether, they're what? They are 90. Okay, so this guy is what? That means this guy, look how deceptive this is. This picture's trying to trick you. This guy's a diameter. Oh, it's so gross, right? I drew this picture really gross on purpose to trick you guys, okay? Look at this. This guy's so gross. This guy's the diameter, right? How do I know that? Well, I know because this guy is 90. This half is 90. So that means this is half of the circle right here, okay? And I am so sorry. That is not at all what that means. Oh, good lord. No, 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 no. I did that completely wrong. I did draw this to trick you guys, but it was to trick you into thinking it was a semicircle. I fell for my own trap. Look at this. This is supposed to be here. This guy isn't necessarily a semicircle, right? We need 180 degrees for a semicircle. So that just means the angle, the central angle here of these guys would be 90, which is also extremely deceptive, right? But it should be 90. That means this angle here, if I come all the way over here, this angle must be half of 90, which is 45, okay? And since these are opposite, we know they add to 180 by our theorem, right? So 45 plus, and this angle, I'll just call x if it helps you guys out. X degrees equals 180 degrees. Okay, this is how I know to subtract. So I'm going to do 180 minus 45 equals, and then for this one we will get 135. Yes, 135 degrees. Okay, that'll be the final answer. So look at this. Be careful about your pictures. Be sure you're using only what you're given, okay? Work slowly, work carefully, work together, all right?